Yeah, so we're gonna, let's see if we can figure out neural nets in the next hour. Maybe 40 minutes. We're taking right. So, wow, that was really cool. I was trying to zoom in on this, and let's try again. Okay. So anyway, yeah, we were yeah, we were thinking of like little neural net tasks where you have like a small set of also everything is Boolean. We only talk about everything is Boolean, plus minus one, and so it seems like it might be a cool task to take like 4 points, 4 binary vectors, arbitrary output labeling, and then try to hand program a neural net that will implement that mapping. It seems like the fundamental problem is that the output unit click, yeah, right. I mean, it's kind of like you have these inputs, and then every layer. So like in this case, the yellow is the inputs. Every layer is producing a new representation, and the fundamental problem is that if you have, like it's hard to tell. I guess like in general, like if you've actually found a representation that is linearly separable, because like our units are computing closeness to their parameter vector, which just means like it takes the input previous layer and it checks that a majority of the indices of the input vector match the corresponding index in the parameter vector. And but it's actually NP hard to, like, if you're just given a set of binary vectors, yeah, if you're just given an arbitrary set of binary vectors, like, it's going to be hard to determine if there exists a vector, like a parameter vector, that they're all, such that that parameter vector is close, is, like Hamming distance less than n over 2 to all of them. And like if you're programming a neural net, it kind of seems like you need to know that. I mean, it's kind of like you obviously need to know that if like you're concerned with like I have to find the absolute smallest neural net. So like you might be able to you might be able to like relax that in some way. I mean, it seems like you could like maybe if you demanded that the input strings like are like say sorted, in the sense that all of the zeros go on the left, all of the ones go on the right. Then like in that restricted version of the problem, it seems like that you could easily compute that. So then like, or I mean like you could also do something like where you just fix the output parameter vector. I mean like, yeah, like again, like if the output parameter vector is all ones, then I mean yeah, like it's easy to determine if your input representation is separable by all ones. Yeah. So like the programming would be like I take my right, like the problem is defined by like the input vectors and their labels. So I first check if if the input represents, what you're checking for is that the Hamming weight of each input vector, whether or not the Hamming weight is greater than n over 2, and whether or not that corresponds to the output label. Right, like if that corresponds to the output labeling, then you're done, and you can just output, this, you just have like a single unit. Neural net. And it might also be kind of like a good conceptual thing where like if you're generating like these problem sets, like these input-output sets, like it might be cool, again, like in the context of like the output unit is fixed, the output unit's parameters are fixed, as all ones. Yeah, it might be cool to like start out with like a like a problem set that is separable, and then you just flip one of the output bits, so like it's no longer separable by the all ones output unit. And then it'd kind of be the idea of like you have to use the hidden layer to like error correct. Yeah, I guess we could like maybe try to do that. It's sure. Yeah. Well, let's just try to do that, isn't it? Okay. Okay. Let's see what happens. I'm going to like do I have that? I thought I had that. Okay. So I am going to copy paste. Oh dang. I'm gonna. It'd be cool if I could just copy paste that part. Yeah. Oh, except yeah. Well, let's. I mean, like, does it make sense to do more dimensions? We'll just stick to 3. It's I guess pretty hairy, like pretty much instantly. Okay. Right. So what we're saying is like, hey, our output unit is always going to be 1, 1, 1. And you know, so like you know, so like we can create a problem set, like a training set, you know, where I mean, like, yeah, for n equals 3, let's see, if you're two away, no, yeah, you have to, so anyway, right, so, like, the output that would, you know, correspond to the all ones would be, this would be a 1 because it's 1 away, and this would be a 1 because it's 1 away, and then, you know, like, this would have to output a -1, and, right, so, this is a training set that is separable by this output parameter. I don't know, I mean, like, should we add another one? I don't know. Just do the all negatives. Right, that should be negative. Okay, so we're still separable. Right, so what we're gonna do is we're gonna flip one of, well, actually, well, yeah, okay. So we can successfully implement this mapping just using a single unit by design. And so what we're gonna do, you know, it's like we're gonna flip one of the, you know, right? We'll do the modified. We'll say that, whoops, I wanted to flip this guy. Boom, he's flipped. See, like now, you can no longer implement this using all ones. It's possible that there's another parameter vector, you know, that's like not all ones that would linearly separate all of that. Or maybe there's not, I don't know. But anyway, we're gonna be like, we're just gonna see if we can implement this mapping I'm gonna put an X over it. Or I'm gonna put a T for target. Right, so okay, so we're gonna try to see if we can implement this map in 4 points. Like we don't care what it does on the other points. Although it is half the input space if you think about it. But anyways, like 4 points, we're trying to implement this output. Right. Okay. Right. So, yeah, I mean, it's really not clear how to implement that. I was going to try to work forwards, but now I'm just back to like wanting to work backwards. So we're gonna go from the output unit, and right. So like if yeah, okay. So we're gonna go backwards from the output unit. Right. The output unit is this. Activation is a 1, and it's by problem definition, it's all 1s. So that means if you want it to be a 1, you can either do 1, 1, doesn't matter, 1x1, and x1, 1, right? So like, right. So we're saying like these 3 inputs are going to have to map to one of these 3 previous layer activations. And this input, it cannot map to any of them. It's not actually clear how to... it's not actually clear. I mean, you could draw another branch with a negative activation. E. Right. You could also try to work forwards. I mean, like... I mean, it kind of seems like, I mean, like, we know, like, all 1s does correctly for this, for these 3. So it's only this one thing that you have to handle separately. Right. I don't think that observation helps. So like one constraint of the first layer is that there has to be one unit that separates, this input from all of the other inputs. I mean, yeah. So, I guess, like, yeah, we could just try to, like, program those. Yeah. Could just try to program those. I mean, that is a necessary constraint. For instance, right, like, there has to be one unit in the first layer, what separates these two inputs. It can also separate other inputs, but it has to separate at least those two. So, yeah, okay, so let's try to make a unit that does that. They only differ on a single input here. So, I think what you'll have to do is you'll have to say the parameters have to be, you have to cancel out the first two parameters. So there's only two ways of doing that. And then, like, that one, right, so like if you do, does that separate them? I know that, wait, yeah, because I'm thinking of addition. This agrees with 2 out of 3 here, so it's a 1 for that, and just 1 out of 3, so okay, so alright, so this separates these two. Yeah, maybe we should like name the separations. So we have this one, that one. So I have like A, B, C. So this separates C. I think, right? Because again, like this goes agree, disagree, agree, so it agrees on 2, so it's a 1, and then it only agrees on this one 1, so it's a negative 1, so it separates C. What about, also by the way, yeah, so it, for this one it outputs a 1, so let's check the other guys to see what it outputs. So it's like agree, whoops, disagree, agree, disagree, so that's a negative. And then this one, it's agree, 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 so that's a 1. So it also separates B. So it separates C and B. Or I mean, like, those are the separations. So we need one for A. We just need to separate A. So we need another unit. I was going to delete these, but it doesn't. Alright, so so we need a unit to do the A separation. So these again agree on 2 indices, so we need to cancel out those indices. Right. So we can just use all 1s actually. And then, right, so if you go here, it agrees on 2, so it's a 1. If you go here, it only agrees on 1, so it's a negative 1, so it separates A. Okay. Right. Yeah. I mean, that's like a necessary property of the first layer. I mean, I don't think it's not the only layer that achieves separation. It's kind of like, it's not clear if we should it's kind of like we have a, I mean, if we're budgeting 3 units in the layer, we have like a spare unit. Well, no, let's just see what the representation is so far for this layer. Right. Okay, so this layer is 1 for the first input. So you disagree, agree, negative for that input. Agree, disagree, agree 1, and then disagree. That's that input for this layer, and then this one is the same as this. 1, 1, negative, negative. And right. And yeah, so that is separable like this, because well, yeah, it's separable, but because all it has to do is separate this one row. Like, we're effectively in 2 dimensions, and so we just have to separate this one point from all of the other points, which you can do with a single unit. However, we were saying, yeah, but we're fixing our output unit to be all 1s. Yeah, so like, can you fix that? I feel like you could, because if you just make the next layers no, yeah, no. Can you fix that or not? I think you can fix that. Like, you just make the next layer. Like, you're just trying to separate this 1 minus. So and we have 3 units, and if you just make them all -1, like, wouldn't that, like, you just say like -1, -1, -1, so like That's going to give -1. It's going to give all -1s. So none of these will be active for this input. But for every other input, it's like 1, 2, and 1. So that would just give all 1s for every other input. Depending on how you count the agreement thingy. Okay. So, but I mean, yeah, I mean, basically what's happening is, like, this is the actual neural net. These all read from the thing. And, right, so, yeah, I mean, I don't think we learned anything from that, other than, you know, you gotta separate the, okay, maybe a better idea would have been to, because I actually, like, I kind of have this implemented, like, or automated, like, I have, like, a script, and you feed it input-output mapping, and then it randomly constructs a neural net by adding layers until, but the only guiding principle is that, you know, all separated pairs have to be, you know, you have to maintain the separation, and then it just goes on forever until it, well, yeah, it checks for linear separability, and then it just keeps going until you, yeah, me, yeah, it seems like what you could do is you could, like, possibly a useful exercise would be, you know, like, you fix a target mapping, and then you, I mean, you can also train these using gradient descent, but, gradient descent doesn't necessarily, well, I mean, it's not doing, like, signed majority computations, so it's, I mean, you can kind of, yeah, yeah, okay, I'm gonna play around with that script, which is, this one. Adding best fit units until computes function. Yeah. And this was doing it kind of difficultly, because we were, for our mappings, the target function, oh yeah, we were inputting all inputs, possible inputs, which is maximally hard, and so yeah, you maintain, yeah, distinguished, Okay, we compute all distinguished pairs for the current representation. Layer representations. Right. Current inputs. Current outputs, while not is linearly separable. Current inputs from current outputs. Compute all the distinguished pairs. For every pair. Yeah, select the weight. Yeah, I don't, yeah, this was using zeros. In the parameters. But I think it's like you should actually just like on the indices where the two pair elements are equal, you should construct a weight vector that like cancels them out, like instead of using zeros. I don't really know if it matters if you use zeros or not. Yeah, I'll just keep using zeros. So anyway, check which pairs are distinguished. Yeah, remove them. Yeah. New inputs. Yep, compute the new inputs. Oh yeah, we were getting rid of unique rows. Maybe we shouldn't do that. Current inputs, current outputs, layer representations, neural net append layer, plot everything. So this is like an example run. It had to add 8 units to keep everything separated. Another layer, another 8 units, 8 units, 9 units, 8 units, 11 units, 9 units, 9, 11, 12, 13, 11. What the hell? Yeah, so we got up to right, yeah, so this is the neural nets. So we got up, so we have 17, or I guess 16 layers. These are the representations that it produced in each layer. The last column being the output label. And those are the weights. Yeah. Okay, so that's I don't know what that is. Yeah. Okay, so yeah, we'll play with those. But we actually want to implement or interpret. Actually want to interpret the thing. Yeah. So I'm going to drastically reduce the number of like input points that we're concerned with. Also, I think I should get rid of the collapsing unique layers, or should I? Well, okay, I'll just reduce the number of inputs that we're dealing with. So, yeah. I think, yeah, so how are you gonna, right, so, pick random subset for target mapping. Okay, so that raises the question of how do you generate a subset using... I think you just do like... yeah, you just do this, isn't it? Random choice from MP, like A range? I don't know why it's A range, but between 0 to power n, and let's just say we want 5 thingies. Yeah, let me, oh my god. I don't want any of this to run, so I'm just going to say while false, right? Oh man, I can't. There you go. Okay. Okay, I just want to check that this actually generates a subset. Why is it taking forever? Okay. Oh, it has a repeat. Is there a way to have it not do repeats? Hopefully. Repeat. 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 Hello. What's gonna... I would like my pop down, please. There we go. Replace. Yeah, that's what you want. Replace equals false. Okay, so now it shouldn't have repeats. Cool. Very cool. We actually don't want it in that shape. We just want it to be like this. Yeah. Okay. And then you can just subset these guys, I think. Yeah, maybe. Right? Is subset all of the columns? Subset all of the columns. Okay, so that should work. Bombs away. So I don't know what this is doing. I don't like it though. Okay, it broke. It broke. Not subscriptable, eh? I'm not sure what that does. Dang, man. Okay. Clearly I broke something. Current inputs. Oh, that's weird. Yeah, that should just say current inputs. Alright. Dang, man. Why won't it work? It's because I'm using inputs somewhere that I shouldn't be. Inputs. That all seems fine. Current inputs. Wow. Equals 4. And we're selecting 5. 1, 2, 3, 4, 5. It's looking like 8 of them. Jeez, man. Yeah. It's because it kept getting linearly separable. Okay, so I just need to keep going until I get a non-separable one. So I'm going to turn this back down. To 6. Okay. True. It's apparently pretty easy to separate 6 points in 5 dimensions. Huh. In 4 dimensions. I mean, like, if you have more dimensions, it becomes easier, right? Or like a fixed... Dang, man. I can't get a... Wow. Okay. Alright. Oh yeah, there's also kind of a... Yeah, okay, I just realized that, like, I'm cheating here. Because I'm fitting, like, I'm fitting like a fool. This is not a majority. Yeah, I shouldn't be doing this part. Yeah, I should get rid of that. Okay. Yeah. I should, yeah. I should, okay, this is gonna, that's not looking good. Right. I think, okay, yeah, let's replace that just with having distance. So like we're assuming the output unit is the all ones output unit. So we're gonna nix this. Old. It's probably just deleted actually, but is, oh my god, is, yes, and it takes us and puts in labels, and so now all we care about is separability according to the all ones parameter vector. And so you can just do somewhere like this one. Yeah. Yeah. Right? Well, I mean, okay, this is a job for AI. Job for AI. That's a joke. All of the jobs are for AI. You know what I'm saying? Oh. Right. So like, what am I doing? Yeah. Okay. So like, in NumPy check if all of the rows of a binary matrix have weight like strictly greater than n over 2. Have how many weight? Well, okay, now let's just say have how many distance less than n over 2 to a parameter vector binary vector w. Bombs away. Whoa, that's like okay, I guess that's fine. Whatever. Seems good. Is linearly separable. Oh no, now I have to adapt it. Dang it. So that would be inputs. did I mess that up? Yeah, I mean, what you need is, okay, these are the Hamming distances. And instead of being NP all, you need, these are the Hamming distances to W. P dot ones shape equals just in. Right? And then distances equals NP dot sum. Right, okay, so this is computing the distance on each row. And then what we need is sine. I don't know what this is saying. How many distances? Because, yeah, like the labels have to be involved somehow. I think it's just do the Hamming distances equal the labels. Oh my god. Yeah, I've like run out of brain glucose. Hamming distances equal labels. So if we have M you know, 1, 1, 1, negative 1, and the other one is 1, negative 1, negative 1, negative 1, and then, so the labels should be, I think they're going to come in like this. So if they're 1, negative 1, then it should be true. M labels doesn't even like that. Oh yeah, that's bad. That's bad. It's like an access problem. np dot equals p dot equal x1, x2. Yeah, but it needs to be like a single. I think you need an all in there anyway. Having distances 1 and 1. So that is not true. What if you just matrix multiply? W. And so that means this needs to be, W needs to be a single column. Something. No, I think you can keep it that way. Okay. Right, so yeah, 1 and -1. And then again, let's print labels. Okay. Is that how I have the labels or not? It's rows and 1. So rows and 1, yeah. So just reshape. Okay, undo all. Okay, so then if you make this negative, right. Okay. Alright, so we're gonna say that that works. And then we'll go run my crazy script. I'm also just gonna delete all of this. It's too much. It's too much. It's too much. Okay. Yeah. Alright, so like now, let's see what happens. Oh. Okay, we're into 1,000 layers. That's cool. Great. Wow. Whoa. Oh yeah. Okay. Right. I mean, I guess kind of as expected. It's okay, if we turn down the number of inputs, like a lot. Let's see what happens. Right. Yeah. Okay. less than max squares and all this stuff. Ooh. But yeah, it just does the same thing every time. That makes sense. That makes sense, actually. Because, yeah, we don't have any randomization in it. Yeah. That makes a lot of sense. That makes a lot of sense. Alright. Like 6 inputs. Right. Right. That's very cool. Yeah. Yeah, I mean, this is entirely deterministic. And, that actually is separable. Why is that not? Yeah, alright. We burned out here.